phase coherence. In other words, we observe these acoustic peaks in the power spectrum of the CMB fluctuations. We have learned also that the perturbations are consistent with adiabaticity, with Gaussianity. Of course, we have detected an almost scale invariant power spectrum. Here, the key word is almost, because we know that inflation predicts a power spectrum that should be close to Harrison-Zeldovich power spectrum, so exact scale invariance, which in this language would correspond to ns equal to 1. But the important point is that we have now observed something which is slightly less than 1, 0.96, and this deviation from exact scale invariance has been seen at more than 5 sigma. I think today must be almost 8 sigmas, which is quite impressive. And this was a prediction of inflation, not a postdiction, a prediction of inflation. So of course, this point is a strong point in favor of inflation. And there is a key prediction that we have not yet observed, which is the fact that there should be a background of gravitational wave. We only have upper bound on the tensor to scalar ratio and little r, and we know that little r should be less than 0.056. So these are important numbers for inflation, and from those numbers we can conclude that single field slow roll models with canonical kinetic terms are the preferred scenarios for inflation. So I should immediately say that this does not mean that more complicated models such as multi-field inflation are ruled out, and as a matter of fact they are not ruled out. It's just that with our present day understanding of the data, they are not needed to explain those data. So even if we restrict ourselves to this simple class of models, the landscape of scenarios remains very populated, and we still have literally hundreds of different single field models. And the question is now, how do we navigate in this landscape, and how do we choose what is the best model of inflation? And in order to answer this question, I have first to define what I mean by the best model of inflation. And this is the purpose of the next slide. So let's start with the plot, the diagram on the top left of the screen. So this is a diagram where on the vertical axis you have the Bayesian evidence of a model. So the Bayesian evidence of a model is a quantity which tells you about the performance of a model, the ability of a model to fit the data without wasting parameter space. So the larger the Bayesian evidence, the better the model in some sense. So this means that good models should lie on the top of this diagram. And on the horizontal line, I have put the number of unconstrained parameters, which is also known as Bayesian complexity. So this is a quantity which allows you to break a degeneracy that exists in the Bayesian evidence, in the sense that you can have two models with the same Bayesian evidence, but with totally different number of parameters, provided some of these parameters are not constrained by the data. And it's clear that we ought to prefer the model with the smallest number of parameters, and therefore this number of unconstrained parameters should be close to 0, which means that the model should lie in this diagram along the vertical dashed green line. So to summarize, a model, to be a good model of inflation, should be at the top of the graph along this vertical green line. And so I have calculated these two numbers that characterize the idea of a model to be a good model of inflation for almost all the models of all the single field models of inflation. that have been proposed since the advent of inflation in the early 80s. So this amounts to almost 200 different models. Each model is represented by a circle. The size of the circle has no meaning here. And well, you see the result on this top left graph. So most of the model are packed in this rectangle. So what I have done is that I have zoomed out this rectangle, and this gives the graph on the top right, where there is again, I'm sorry, a rectangle. I have again zoomed out this rectangle, and this gives the graph on the bottom left. And finally, this rectangle that you can see here has been zoom out again, and this gives the region that contains the best model of inflation. So again, the best model should lie at the top of the graph in the vicinity of this green line. And if you look at the models that are present in this part of the graph, you typically find the Starobinsky model. So a conclusion that you can draw from the Planck data is that plateau inflationary models are the winner. They are exemplified by the Starobinsky model. This is not the only plateau model, I should say. There is a group of models that have a potential shape which is similar to Starobinsky, but typically this is the model that seems to emerge from the Planck data. So a plateau model has a potential with this form, with a potential which flattens out at infinity. So in this model, the field slowly rolls down its potential from the right to the left on the plateau, which is very flat. So this is typically the kind of information that you get on inflation from the Planck data. Another aspect of this observational status is that inflation does not only consist in the phase of accelerated expansion, but it's also very important to be able to stop inflation. And this is, of course, the phase of reheating. So usually this happens in the following way. So your field slowly rolls down its potential, but at some point, the potential turns out to be no longer flat enough to support inflation. In that case, inflation will stop. Usually this happens in the vicinity of the ground state of the system, so the minimum of the potential. In this regime, the field oscillates. It decays when the lifetime of the inflaton field has been reached. It decays into some decay products, and these decay products are supposed to thermalize, and this is how you start the radiation-dominated era at a given temperature, which is known as the reheating temperature, that can be inferred from the knowledge of the decay rates of the inflaton field. And of course, we would like to learn about this phase, which is absolutely crucial, and we would like to constrain observationally this phase of evolution. So in the framework of single fields models, there is a fact is that curvature perturbations are conserved on CMB scale, so they are in some sense insensitive to the details of the reheating. So this may be seen as a good news, because it means that whatever you have obtained for the power spectrum during inflation, it will not be affected by the reheating, so you can draw some generic conclusion. But on the other hand, it can also be seen as a bad news, because it means that you cannot really use the power spectrum, at least on large scales, to learn about the details of the reheating and to learn about the coupling of the inflaton field with the rest of the world. There is, however, one thing that you can do is, and it is based on the following remark. If you change the duration of the reheating, or if you change its equation of state, you will move the observational window along the potentials. And given that we have constraints on the shape of the potential from the measurement of the spectral index, this is something that you cannot do arbitrarily. So this means that there will be duration of reheating or equation of state, which will be in contradiction with the data that we have. And in this way, you can learn a little bit and derive mild constraints on reheating. And I have just illustrated what I mean exactly on this plot. So this is a plot of the tensor to scalar ratio versus the spectral index for large field models. So the potential is just some power law with an index P. For a given index P, for instance, P equal to 1 or P equal to 2, m square phi square, all the predictions, all the thorough predictions are along a straight line. But if you change the duration of the reheating, you will get, so for different reheating temperature, you will get a spread along that line, and some of these, some values of the reheating temperature are within the Planck contour, and some others are outside. So this means that there is, with the CMB data, there is a possibility to obtain mild constraints on reheating. And in fact, you can very easily realize that there is only one parameter that you can constrain, which is the reheating parameter, which is given by this formula, where rho reheating is the energy density at the end of reheating, or it's the reheating temperature, if you prefer. Rho n is the energy density at the end of inflation, which is known if you know the model of inflation. And W reheating is the mean value of the equation of state during reheating. And this parameter is the only one you can constrain using this method. So I have no time to really discuss the origin of this parameter, but there is a consistency check, which I think is very intuitive and which may help to understand why this parameter is relevant. And the consistency check is the following. It is clear that there is no mean with this method to distinguish between instantaneous reheating and between a reheating which would proceed with an equation of state, which is that of radiation, because in that case, you cannot distinguish reheating from radiation. And you can check indeed that instantaneous reheating, which means rho reheating is equal to rho n, means that R is 1. And if W is 1/3, if you have a phase of reheating with a radiation-dominated era equation of state parameter, R is also 1. So these two things give the same value for the reheating parameter, which is not a proof that this parameter is correct, but which I think makes intuitive the fact that it is relevant. So this means that, so it may be surprising that such a process as complicated as reheating can be described with one parameter. Of course, it's possible to describe it with one parameter only if you use only the CMB data. And it's a bit like reionization. Certainly, reionization in the early universe is a very complicated process from the atomic physics point of view, but nevertheless, you can describe it as far as CMB data are concerned with one parameter, which is the optical depth. So this is exactly the same here. So any constraints on the reheating using CMB data will take the form of a posterior distribution on the reheating parameter. And this is what you can get from the Planck data. So let me explain this plot. So on the vertical axis, you have the Kullback-Leibler divergence. So this is a quantity which tells you about the difference between the posterior and the prior distribution. See, if the posterior distribution is very different from the prior distribution, it means that you have acquired a lot of information. So the larger this divergence is, the better the constraints are. And on the horizontal axis, I have put the Bayesian evidence, or the Bayes factor, which, as I have already said, describe the performance of a model. And each point here is again one among hundreds of single field slow roll models. And here the yellow band represents the mean value of this Kullback-Leibler divergence. And you see, you find a quantity of information which is something like half a bit. And if you go now to Planck 2015, you find that this value is almost 1. So in fact, there is an increase of 40% on the constraints that we have on reheating from Planck 2013 to Planck 2015. And so we have some constraints on reheating, and they are quite model dependent, I should say, and they are mild. Okay, so this concludes what I wanted to say about the observational status of inflation using the Planck data. So there are essentially three punchlines. First, single field models are favored. Second, plateau inflationary models are the winners. Third, we have mild constraints on the reheating phase. So based on those results, I think it's timely to try to discuss and try to assess the theoretical status of inflation based on what we have learned from Planck. So for the inflationary mechanism, so the phase of accelerated expansion in the early universe, we all know that it rests on general relativity, which is a very well-tested theory. So it seems to be a very robust theory. But more precisely, we know that we can get acceleration, that is to say inflation, because the pressure terms appears in the acceleration equation for the scale factor, as you can see here. And the fact that the pressure terms appears in this equation is really due to one of the fundamental principles of GR, namely that every form of energy weights in GR, including the pressure. And usually when the tests of GR are derived, they are not very sensitive to that term, because usually this term is very small. In fact, this term plays a crucial role in 4 situations, at least to my knowledge. Inflation, of course, dark energy, but dark energy is almost the same as inflation, in neutron stars, and in Big Bang nucleosynthesis. So let me, and so these four fields, or these 4 examples, can be used to test whether the 3p terms is really there in nature. And let me show you what can be done with the BBN. So in this paper, people have tried to test how much the 3p term is important for BBN. So what they have done, they have introduced an ad hoc modification of the acceleration equation with a chi parameter, which is completely phenomenological. And using this equation, they have rederived the abundance of the nuclear elements produced in the early universe. And you see a plot of chi versus eta. And so the color line are the contour level for different elements, helium-4, lithium-7, deuterium. And the constraints that they obtain are represented by this circle. And you see that this is incompatible with chi equals to 0 and compatible with chi equals to 1. So in some sense, the punchline here is that the BBM tells you that indeed pressure gravitates, and therefore, based on this conclusion, we can say that the accelerated expansion during the early universe inflation is I think, a well-tested scenario for the early universe. There is also the structure mechanism for inflation. So here the idea is basically the following one. At the beginning of inflation, we have quantum fluctuations of the inflaton field and of the gravitational fields. The two are coupled through Einstein equations. And those quantum fluctuations, they are amplified by gravitational instability and stretched to cosmological distances by the expansion. So if inflation is true, it means that all the structures that we observe in our universe, the galaxies, the CMB anisotropies, are nothing but quantum fluctuations. And all that is taking place at very high energy, possibly 10 to the 15 GeV. So at first sight, it may seem as a very strong claim, But I would like to draw your attention to the fact that in fact, it can be viewed as a mechanism which is in fact very conservative. Because this mechanism is in fact very similar to the Schwinger effect. So the Schwinger effect is an effect in quantum field theory, which was computed by Schwinger in the 50s, and which consists in the following. You have a quantum field associated with electrons and positrons, fermions, and this fermions is in this quantum fermions is in interaction with a classical source, a classical electric field. And Schwinger has computed as a result the number of particles that are created due to this interaction. And the amplitude of the effect is controlled by the strength of the source, which is the magnitude of the electric field. And there is a one-to-one correspondence between the Schwinger effect and the inflationary mechanism. The role of the electron and positron field is played by the quantum fluctuations of the inflaton and the gravitational field. The exterior classical source is the classical background, the scale factor. And as a result, when you compute the two-point correlation function of the fluctuation, the power spectrum, you find an amplitude which is controlled by the strength of the source, which is the expansion rate during inflation h. So this is really the same thing. And in addition, there are also other effects which are very similar, such as the Hawking effect, the dynamical Schwinger effect, the dynamical Casimir effect, which has been seen in the lab. So in fact, this inflationary mechanism, it belongs to a very well-known class of effects in quantum field theory. And I believe this mechanism is quite robust as well. So I would describe the inflationary mechanism for cosmological perturbation as robust as well. So given this, now let's try to discuss what are the theoretical open issues. So here it's a bit subjective. This is what I see as important questions to be addressed, but I see three different questions that could be that should be addressed in order to improve our knowledge of inflation. The first question is obvious. I think we would like to relate this phenomenological model of inflation to high energy physics. So this is the question of the physical nature of the inflaton field, and this is the question of model building. So some questions that might be asked are the following. We have seen in the lab only one scalar field, which is the Higgs boson. So an obvious question is, has inflation some connection with the Higgs? Another question, which is also interesting, is that inflation probably takes place at very high energies. And from what we know about physics beyond the standard model, and here I'm thinking about, I don't know, supersymmetry, supergravity, string theory even, we know that all this extension contains many scalar fields. And therefore, there is a question that arises is how a single field description, which is extremely simple, can emerge from a situation where there are many degrees of freedom. And a corollary to this question is if this is true, that there many degrees of freedom are probably at play in the early universe, can we observe the effect of these extra degrees of freedom, for instance, by trying to probe more precisely the early universe? So by extra degrees of freedom, here I mean models beyond vanilla inflationary models, such that multi-field inflation. We can think also about the role of the gauge fields during inflation and so on. So this is a first group of very important questions that we can ask. Another obvious question is, of course, we would like to know more about how inflation ends. So this is the question of the reheating, of the preheating, how thermalization takes place, and so on. And finally, there is also the question of the inflationary mechanism for structure formation that I was described previously. And here the question is the quantum to classical transition. So initially the perturbations are quantum. When we analyze them, they are classical. How does this transition proceed is still not known. So this brings into the game fundamental questions about quantum mechanics. So this shows that inflation is not only a successful scenario for the early universe, it's also a playground for people studying fundamental aspects of quantum mechanics. In fact, inflation is the only known system, at least to my knowledge, that uses general relativity and quantum mechanics to derive the predictions, and where high accuracy data are available. When these two things are satisfied, to my knowledge, the only system that I know of is inflation. And the observational tools that we have to address this question are non-Gaussianity, that I will not use here, gravitational waves, and PBH. So what I'm going to do for the end of the talk is to try to see how gravitational waves and PBH can be used to further test the vanilla scenarios. And here I should make a warning. Of course, gravitational waves and PBH have been used, and quite recently, to discuss the models of inflation that go beyond vanilla model. These are very interesting and important works. Unfortunately, I have no time to describe those works. I hope they will be covered in the other talk. So here I will just focus on on what we can learn about vanilla models using those observational tools. But of course, this is just due to lack of time. It does not mean that the other subjects should not be studied. Quite completely the opposite. I believe these are very important topics as well. So let me now.
Sorry, Jerome. Just to say 6 more minutes.
Okay. Perfect. Thank you.
Okay.
So let's come to the last part. So going beyond the present state of the art. So an obvious way to go is to check a key prediction of vanilla inflation that has not been checked, namely the presence of a background of gravitational waves. So one way to go, and this has been discussed, of course, at length, is through the measurement of the polarization B modes of the CMB on large scales. So this is one way to go. There are different missions ongoing, ground-based missions or satellites such as Lightbird that will be launched in the following years. Very roughly speaking, the target is to reach R10 to the -4. Maybe this is a bit optimistic, maybe slightly less than this. And we know that for the Starobinsky model and for the other Plateau inflationary model that are the best model according to the Bayesian analysis that I have presented, R is slightly more than 10 to the -3. So if we are lucky enough, we should maybe see something with this next generation of experiment, and we could learn a lot from a possible detection. We would learn about the energy scale of inflation. We could test the consistency check of inflation, which would be a final proof that we have to deal with vanilla model, or on the contrary, we would maybe observe a violation of this relationship. We would measure the first derivative of the potential. We will have access to the field excursion, and this would greatly improve model selection and constraints on reheating. So really, of course, this is like a Rosetta Stone for inflation. It would be very useful to be able to detect this background. What about a direct detection? Now, we could try to detect directly with the gravitational wave observatories the background of gravitational wave produced in the early universe, and typically we would obtain this graph. So this is the omega gravitational waves versus the frequency with the different observatories, and this is the power spectrum of primordial gravitational waves. So this is scale invariant here, and then at some point you have a break here. That can and the tilt in this regime can be blue, can be red or blue. And what would we learn could detect this, directly detect this background of gravitational wave, I think we would learn about reheating, because this break occurs at the reheating temperature, because we have a break in the power spectrum, because this corresponds to very small scale that re-enter the Hubble radius just after inflation during reheating. This is why we have this break at the reheating temperature. And the slope of the power spectrum in this regime gives you directly access to the equation of state during reheating. So a direct detection, if possible, of course, a direct detection will give us pieces of information about reheating. There is, of course, we expect a background of gravitational waves from preheating effect, namely the fact that we have non-perturbative effect during preheating. So this is quite difficult to predict exactly. This is very model dependent, but we typically expect a power spectrum with a peak in this regime. I am running out of time, so if you want to learn more about this aspect, which I believe is very important, you can look at these two papers. But this could be also a way to probe preheating. So let me just mention that these gravitational waves are second-order gravitational waves, contrary to the previous one. Namely, during preheating, you have non-perturbative effect, so you have a large growth of the scalar perturbation, and the scalar perturbation can source gravity waves, and these are those gravity waves that we could observe here. In fact, and this is the last point that I would like to discuss here, we also have gravitational wave and primordial black holes from metric preheating. And maybe this allows me to say a little bit more about this non-perturbative effect during preheating. So before this was background preheating, now this is metric preheating, so the perturbation themselves. So the mechanism is very simple. Well, when the field reaches the minimum of this potential and oscillates, the potential can, except if there is some unknown or extraordinary symmetry, the potential is always can always be approximated by a parabola. And during this phase, it's known that the universe behaves as a matter-dominated universe. During this phase, you can show that the perturbations obey a Mathieu equation. So an equation which contains exponentially growing solution. And in fact, you can show that for modes that satisfied this inequality, I'm going to explain what it means exactly, the modes of the perturbations fall into the first instability map, the first instability band of the Mathieu chart here. And in that case, there is an instability and the perturbation, the density perturbation grow like the scale factor. So it grows a lot. In fact, satisfying this inequality means that we deal with the following mode. This is a plot. This is my last plot. So I'm coming to the conclusion. This is my last plot. So this is a plot of the physical scale that are relevant during inflation versus time. This is inflation. This is the end of inflation. This purple line is the end of inflation. And this is here reheating, matter-dominated universe. So this is the reheating. The solid line is the Hubble radius. And the dashed line is this new scale that I have introduced, which is the inverse of the square root of the mass of the field at the minimum of the potential times the Hubble radius. And being into the instability band means being between those two scales. So you see that the mode, they exit the Hubble radius during inflation, and then during reheating, they re-enter the Hubble radius and they penetrate in the instability band. So here we are talking about modes that are very small compared to the CMB modes. The CMB modes, they leave the Hubble radius typically 50 e-folds between the end of inflation. Here we talk about modes that leave the Hubble radius less than 10 e-folds before the end of inflation. And those modes, they will undergo this drastic instability. And as a result, since we have a growing density contrast in a matter-dominated era, this will lead to the production of ultralight primordial black holes. This is a generic prediction, in fact, of any single field inflationary models. And remark that usually people try to invent mechanisms, they distort the potential, they consider multi-field inflation, ultra-slow roll inflation, which are interesting scenarios. But here you have, in some sense, the production of black holes for free. This is a generic prediction of the simplest models of inflation. And so studying the consequences of this PBH production would also be a way to probe for the future and to probe the simplest models of inflation and to improve our knowledge of vanilla inflation. So I just come to the conclusion, since I think my time is over. Well, I just very briefly repeat what I have said. So single field slow roll models are solid, robust, and falsifiable scenarios of the early universe. I think something important is that they have made predictions that have been verified. They are preferred models given the Planck data. There are still open issues, I think, that I have listed and discussed. There are still predictions that have not been verified, even for those simple models. The best example being the presence of a gravitational wave background. And recently, I had no time to discuss it, but recently, additional mechanism in the context of non-minimal models of inflation have been studied. I hope this will be covered in other talks. And so to see which incarnation of inflation we deal with, gravitational wave and PBH, and of course non-Gaussianity are keys to really study which incarnation, which realization of the idea of inflation we deal with in the real world. And I just stop here. Thank you very much.
Thanks a lot for this very nice talk. We are slightly over time, so we have time for only a couple of questions. I see Anish has raised his hand.
Hi, thank you for the nice talk. I have a couple of questions. So one question is that when you define the parameter R rad, which is the ratio of the energy density before the radiation domination era started to the energy density when it started. So and then you predict some points on the NSR plot in the very beginning, right? You said
yes,
for different value of that is threshold. So that NSR plot, is it generated due to from the Planck lambda CDM analysis, or is it the NSR plot has been redone from, including that extra free parameter which you are proposing? Because the usual lambda CDM NSR plot that we use for Planck are the 6 parameter plot from the lambda CDM, right? So now you have one more free parameter.
Yes. No, this has not been. So you mean the contours, right? The Planck contours.
So,
No, it has been done in the context. So it has been done not strictly speaking, not in the context of lambda CDM. It has been done consistently, meaning with a slow roll power spectrum. So the free parameters are not NS and the amplitude, they are the slow roll parameters. And the reheating parameter is one free parameter, which is included into the analysis.
So so this is like a 7 parameter fit, right? To the CMB data. Am I correct? The standard lambda CDM plus this.
Exactly, because from the slow roll point of view, you have the yes.
So then can you also comment on how much, like what is the best fit value of this number of E-folds during reheating, and because when you do the statistical analysis, you must get some best fit value as well, right? So this should correspond to some.
So this is a Bayesian analysis, so there is no best fit value in some sense, but of course, this is what I have shown here. You see, so first of all, it's very model dependent, but from the color code, you can get the value of the reheating parameter for a given model that you obtain from this analysis. I think it's exactly your question. Of course, going from the reheating parameter to the physical parameters that characterize the reheating, namely the reheating temperature and the equation of state parameter, is not obvious, right?
I see. Okay. And another thing I wanted to ask you regarding the your last plot where you showing the detectability of primordial gravitational waves.
Which one?
I think the last.
No,
yeah, at the end, the detectability of whether you can. I mean, later. I think.
Later? I don't.
Yeah.
This is my last plot.
No. I think slightly before this one, where you had primordial as gravitational wave spectra.
This one, you mean?
Yeah. Yes. So here, I see the value of omega GW at this frequency scale 10 to the power -2 is something around 10 to the power -16, right, or something like that. So this is an assumption, right? I mean, or
yes,
like
yes. So this is an assumption because you see it's written alpha attractor model. So here there is an assumption about a model of inflation. This is alpha attractor. So of course, if you change if you change the model, the horizontal line will move, could move depending on the model. Yes, absolutely.
So that means there is a degeneracy between the detectability using the last kind of I mean on the right hand side of the spectrum and this initial value initial value that you're taking, right? For example, it can go down and still you cannot detect.
Yes, if you
initial value. Yeah.
Sorry, I could not hear you very clearly, but
I'm saying
it was cut. The sound was cut. I'm sorry.
Oh, sorry. I'm sorry. I was just saying. I was just saying that if the initial value is a little bit lower, then we might not still be able to detect it, right?
Yes, sure.
Even after boosting. So I think the main conclusion is that we can have a boost, and I mean,
yes,
if
but
the initial is also very large, then we can also detect.
But let me comment on this. You said we can have a boost probably because of that. You mean because the spectrum is blue here, but this corresponds to equation of state during reheating that are negative. So they are not the most. The most reasonable equation of state. I would describe them as exotic equation of state during reheating. So typically, if I take an equation of state which is 0, which corresponds to matter domination, you see that the power spectrum has a index which is -2. So this would correspond to this situation, and of course the signal would go down and would be even more difficult to detect.
I see. Thank you.
Okay, maybe we can wrap it up. We are 5 minutes over time. Thanks a lot again to Jerome.
Thank you very much. So
we can.
I stop sharing my screen.
Yes, we can move on with the next speaker, who is Rishi Khatri. Can you share the screen, Rishi? You around?
Yes.
Yeah.
Let me share the screen.
Great. Okay. Rishi is going to tell us about dark neutrino interactions and CMB modes. The format is 20 + 5, and I will tell you when there are only 5 minutes remaining. Thanks a lot. Pleasure see yours.
Yeah, should I start? Yeah, okay. So I am going to be talking about this work which we did with Shubhajit Ghosh and Tuhin Roy. Actually, all the hard work is done by Shubhajit Ghosh, who was a PhD student here at TIFR. Now he's a postdoc in University of Notre Dame, and is based on these 2 papers. So I'll be talking about mostly post-inflationary universe. So all my talk is about post-inflationary universe. And in particular, I will point out an interesting connection that we found which connects the CMB tensor modes as well as with the Hubble tension in this dark neutrino interaction or DNI cosmology framework. So, so I think everyone knows that a lot of effort has been spent in trying to detect the CMB B modes, which will be, in particular, we want these primordial B modes, which are the imprints of primordial gravitational waves on the CMB. There are other B modes also like lensing, but primarily the big prize is this primordial gravitational waves. And there are lots of ground-based experiments, balloon-based experiments, and also space-based experiments. There are space-based, actually, there are a lot of proposals. So there's only one experiment which is funded, which is Lightbird. A lot of money and effort has been spent. So we started thinking about, suppose, let us take an optimistic view and suppose, detection of gravitational waves is just around the horizon. Suppose we detect gravitational waves and measure them precisely. And what can we learn? Apart from the obvious thing that we learn something about scale of inflation, that these are inflationary gravitational waves we are detecting. But can we learn something more about fundamental physics or post-inflationary, from the post-inflationary evolution of these gravitational waves? So, for example, the question we can ask is, suppose we detect a spectrum and we get a blue spectrum. Does that rule out a large class of inflationary models? Because most inflationary models would predict a scale invariant spectrum. It has to be consistent with the scalar power spectrum that we measure. So example, for scalar CMB temperature and polarization power spectrum, we can actually constrain lots of particle physics beyond standard model particle physics. We can constrain whether there is extra radiation in the universe, whether there are new interactions, whether dark matter decays or annihilates. So a lot of things we can do with, if we do, because we have measured this CMB temperature and polarization very, very precisely. And because the early universe is so simple, that we can calculate this CMB temperature and polarization power spectrum very, very precisely, theoretically also. And that allows us to do very precise tests of what kind of new physics can be present in this early universe. So can we do similar thing with B modes? But can we constrain particle physics by precise measurement of these tensor modes or the CMB B modes? And do they have a qualitatively new information compared to the scalar CMB temperature and polarization and isotropies that we have already measured with Planck and also many ground-based experiments and balloon-based experiments? So it turns out the gravitational waves, actually, the evolution of gravitational waves is much more simpler than the scalar perturbations. In particular, they interact very weakly with matter. So the evolution is given by this very simple oscillatory equations. HQ is the tensor amplitude. And this is an oscillatory equation with a damping term. And damping is coming, the solution you can write down. And the damping is coming just because of the expansion of the universe. So gravitational waves, they are radiation, and from the solution we directly see that they redshift just like radiation. The energy density will go as redshift to the power fourth. And through most of the matter is transparent to the gravitational waves. So dark matter and including photons, which are tightly coupled before recombination, and post recombination there is very little energy density in photons. So most of the stuff of the universe does not really influence gravitational waves. But there is one important constituent of the universe which has a dramatic effect on these gravitational waves, and those are free streaming neutrinos. This was first pointed out by Bond in numerical calculations and then studied in more detail by Weinberg. And what happens is that gravitational waves, they introduce an isotropic stress in the neutrino field. They produce the anisotropic perturbations at the neutrino on horizon scales. But for neutrinos are free streaming, and they're streaming at the speed of light. So as soon the gravitational waves are generate anisotropic stress in the neutrinos, but this stress immediately gets dissipated. This is similar to dissipation of sound waves, scalar modes by photon diffusion, also known as Sill damping for the scalar modes. But here you need some relative, for dissipation of gravitational waves, we need a relativistic free streaming species. We need something that is basically which can free stream at the speed of light. And the reason is that gravitational waves are traveling waves, whereas these sound waves in these that we see in CMB, they are standing waves. So gravitational, this is what I just said. So gravitational waves source an isotropic stress in neutrinos, and free streaming of neutrinos destroys this anisotropic stress, and which results to damping of the gravitational waves. So what this means is that this equation that I wrote down earlier gets modified. It gets a source term or a sink term in this case, which is sourced by this anisotropic stress in the neutrinos. And the effect is quite dramatic, actually. I will just show you a plot. It is actually about 50% of the energy in gravitational waves is dissipated for gravitational waves for the modes which enter the horizon during radiation domination. And again, this is all happening in standard cosmology. There is no new physics until now. Right? And then gravitational waves, because these are tensor modes, they generate a quadrupole anisotropies in the at the time of last scattering in the recombination surface. And this scattering of this quadrupole by electrons, the Thomson scatterings, generates polarization. And in particular, the gravitational waves generate B-mode polarization, which is not sourced by this polarization patterns, which have odd parity, which cannot be sourced by scalar modes. So this is the smoking gun for presence of tensor modes in the early universe. And this is what really the holy grail of CMB experiments right now. And just to show you, so I have brought this CMB's BB mode power spectra here. So this blue line is the solid blue curve is the lambda CDM model. And then this dotted red line is if there is no damping. So I have stopped the neutrinos from free streaming by modifying the Boltzmann equations. And you see that there's enhancement in power. And this enhancement is more dramatic as the smaller, higher in L that you go. And there are other curves also, which I will talk about later. So this is by introduce some interactions between neutrinos and something else, in which in this case, this is dark matter. And this U zeros are just the strength of this interaction. And then you see that on small scales, again, you have enhancement. Because we are introducing this interaction, there is still this stopping of neutrinos is not perfect. So this effect is a little bit less than what will get. There are absolutely no damping. So I will come to this in a little bit later. And for comparison, I have also showed a blue spectrum. So this, if you stop the neutrinos from free streaming, it will mimic a spectrum which is actually such that it will be similar to a initial blue gravitational wave spectrum plus free streaming neutrinos. Here I have shown actually the fractional difference in the BB mode power spectrum. And here you see that actually the very small scales, the modes which are entering horizon during radiation domination, the effect is of almost 50%. And this topmost curve. And then as you decrease the strength of neutrino interactions, this effect becomes smaller and smaller. And this effect is similar to this NT equal to 0.05. That is the blue spectrum of primordial gravitational waves. So qualitatively, this effect is similar or degenerate. But of course, the details are different. If we can measure these things precisely, we can distinguish. But that is an open question. Okay, so the only term which comes, source term which comes in this evolution of gravitational waves is this anisotropic stress in the free streaming relativistic species, which is just neutrinos in the standard physics. So you can modify primordial gravitational waves. If you introduce additional radiation, you will have more dissipation. There will be even more damping of gravitational waves. This has been studied many years ago by these people. And we decided actually to stop neutrinos from streaming, then it will enhance the gravitational waves. Basically, you don't have the damping that you get. So your power at small scales will be 50% more than what you will have in the lambda CDM. This is what we were interested in. And there are many ways to stop neutrinos from streaming. People are studying many ways. And usually, gravitational waves do not really care about what kind of interactions neutrinos have, the details. They just care about whether neutrinos are free streaming or not. Because if they are not free streaming, then you cannot generate anisotropic stress and there is no damping. So this is really a clean probe of whether neutrinos are free streaming or not. So it's just a test of neutrino free streaming. And just to make things concrete, we decided to cook up a particle physics model. So where neutrino interacts with a small fraction of dark matter. And depending on the mediator mass, so dark matter mass is much, much higher than the energy of neutrinos. So we are in the non-relativistic limit. And depending on the mediator mass, you can have two kinds of behavior. The cross section can be temperature independent or momentum independent, and that's what I call use superscript 0. Or it can have a temperature dependence, which is like T square, the temperature, neutrino temperature square, which I call label this U sub 2, U sub superscript 2. And this is just a normalized interaction strength. I have normalized with Thomson cross section and mass of dark matter. So this is just a dimensionless parameter. So higher the parameter, the stronger is the interaction, and more is the neutrino stopping power of this dark matter. Right. So we can ask then the question, what value of this U0 when this mean free path of these neutrinos is equal to the Hubble, to the horizon rate. And this is what I am plotting here. For example, if you look at, let us say, red curve, U sub superscript 0, when it is 10 to the minus 2 horizontal line, then above redshift 10 to the 4, neutrinos are not free streaming. The mean free path of the neutrinos is, smaller than horizon scale. And at the lower redshift, the mean free path of the neutrinos is higher than the horizon scale. So below redshift of 10 to the 4, neutrinos are free streaming. Above, they are not free streaming. So there's a transition from non-free streaming behavior to free streaming behavior as we go down in redshift. And that introduces a scale dependence in this power spectrum. So this is what, let me try to finish this quickly. So because I also want to go to the Hubble tension. So what I have plotted here is the evolution of the anisotropic stress. What I have plotted here is the anisotropic stress from neutrinos for different scenarios. So solid lines are lambda CDM, and you see that where the neutrinos are free streaming. So let us look at this rightmost curve, the red curve, which is a very small scale mode. So Q or the K mode is very large. So this is the mode which is entering the horizon during radiation domination. Right. So as the mode starts entering the horizon, these gravitational waves, the transfer modes, they generate a large anisotropic stress in these neutrinos. And as it enters the horizon, this stress gets dissipated. So you have increasing anisotropic stress, which then gets dissipated as it enters the horizon, and then it just oscillates with smaller and smaller amplitude. If you go to a slightly larger scale mode, Q of 0.01, then the effect is less dramatic, because as you go down in redshift, this anisotropic stress, it is proportional to, the effect is proportional to the energy density in neutrinos. As we are going down in redshift, the relative energy density in neutrinos is decreasing. So again, we see that, so in the blue curve, there's again, you generate an anisotropic stress and then it dissipates. Okay, so 0.01 is actually also entering during radiation domination. So then if you introduce interactions, that is this U0 and U2 curve, and I have chosen a particular value so that for Q 0.1, when it enters, neutrinos are not really free streaming, they are tightly coupled. Then we see that this effect completely goes away. So these dashed and dotted curves, you don't really develop any anisotropic stress, so there is no damping of gravitational waves. But if you go to slightly larger modes, which are entering horizon later, then because as the universe is redshifting, the number density of dark matter is going down. So neutrinos are starting to, they're getting less and less tightly coupled with the dark matter. And you start seeing some effect of this neutrino, damping effect of neutrinos, but it is still smaller than the lambda CDM value. And for very large modes, there is almost no difference from lambda CDM. And this is the gravitational, what is happening to the gravitational wave modes, so different gravitational wave modes. So again, so you compare the lambda CDM model with the interacting model, and you see that it is not really that clear in that. I will just show you a zoomed in version. This is just to give you an overview. So gravitational waves, they get damped as they enter the horizon, and then they oscillate and redshift just as radiation. And there's a difference. The amplitude, when you introduce interactions, the amplitude of these oscillations is large. The amplitude of gravitational waves is larger compared to lambda CDM. This is, I have just zoomed in on the this oscillating part, and you see that with interactions, this amplitude of the gravitational waves is larger. So the CMB,
sorry, Sorry, just to say 5 more minutes.
5 more minutes? Yeah, okay.
Yeah.
And here we see that, okay, so I'm showing the fractional difference in the CMB beam was introduced. And again, you see that there's enhancement on small scales. There's enhancement also, good thing is there's also enhancement in between L of 10 and 100. This is the first peak. And this is more easily observable. The very small scales are, this is fractional difference. So you see a large difference, but the absolute amplitude is very small. And we have to actually D-length to get to this very small scale modes. So this was for scale independent cross-section or temperature independent cross-section. This is this U2 where the cross-section is the temperature square dependence. Where you get, the shape is slightly different, but the effect is similar. And again, so this is just saying that if 100% of dark matter cannot interact really, because then the neutrino pressure will modify the dark matter power spectrum. And which are, so there are very strong constraints on 100% dark matter interacting with the neutrinos. But if only a small fraction of dark matter interacts, then all these constraints do not apply. So now there's an interesting connection. You say, okay, we already see that, okay, we are affecting dark matter and maybe neutrino free streaming is also affecting scalar modes in some way. So let us look at that in detail. So what happens, what is happening to the scalar modes? And it turns out that actually this can solve the Hubble tension. So just, okay, I will just not skip this. So we have CMB and we measure the power spectrum, the CLs, by decomposing into spherical harmonics. And the CMB oscillations are described by a very simple oscillator equation. It is a little bit more complicated than what we have for gravitational waves, but still we have oscillations. So theta is the temperature anisotropy. We have the sound speed CS, and we have a damping term, which is coming because of baryons. And then we have a forcing term. So forcing term is basically everything which gravitates. So phi and psi metric perturbations are here. So everything, dark matter, dark radiation, neutrinos, anything that has gravity, it will come in the forcing term. In particular, neutrinos have, so the solutions are these oscillating solutions, which everyone knows, cosine k c eta. So neutrinos actually have very interesting effect. So just like dark matter perturbations in neutrinos, they decay away as neutrinos free stream, as they go to, as they enter the horizon. Scalar perturbations in neutrinos also decay away because neutrinos free stream. Scalar perturbations also are damped by the neutrino free streaming. So all the perturbations in neutrinos, they decay away as the mode enters the horizon. What this means is that, so the scales which are of order horizon, as they are entering, this forcing term, neutrino contribution to the forcing term, it is like a step function. Because neutrinos are free streaming at the speed of light, which is much faster than the sound speed. So for this oscillator, it is just like you have introduced a step function like forcing term. What that does is it introduces a phi nu, a phase shift in these oscillations. This has been studied very quite well by many people. But I think the way we study it is a little bit more cleaner than the way people usually do it. So normally people change the number of neutrino species and see how this phase shift changes, and that is how they try to extract the effect of neutrino free streaming from these oscillations. But what we do is much cleaner. We just stop the neutrinos for free streaming, and that directly comparison with free streaming case directly tells you the effect of free streaming of neutrinos on these oscillations. When we observe this pattern as it exists in the time of recombination, and we project these three-dimensional oscillations into a 2 dimensions by these Bessel functions. So in the CMB power spectrum, what we observe is these L modes, which are related to these K modes by this dA. dA is the distance to the last scattering surface. At some scale R star, which sound horizon, for example, let's scale at the recombination surface appears to us at angle on angular scale theta, which is related to scale L by dA over R star, or dA times K, where K is the K corresponding to R star. And the acoustic peaks correspond to these peaks of this cosine function. And so normally people ignore phi nu, but we should not ignore phi nu because it shifts the peaks where they should be. So the L peaks, where the L modes, where you see the peaks, is related to this, is given by this formula. So it depends on this distance to the last scattering surface, which depends on the recombination, the expansion history from recombination until today. It depends on R star, the sound horizon, which depends on the expansion history from Big Bang until recombination, and it depends on this phi, which is the phase shift. And it turns out, so this is the Hubble tension. You want to CMB measures a smaller Hubble constant than choose, and if you try to increase the Hubble constant by keeping the things constant, for example, keeping the universe flat and keeping physical densities of different species constant, it turns out increasing the Hubble tension just adds a constant term to the Hubble parameter, h of z. And because h of z is larger at larger redshifts, the effect is actually very small. It really modifies only the late time expansion history. In particular, if you increase h0, you only increase dA, R star remains unchanged. And because you change dA, the L peak will change, where you observe the peak of the CMB, L peak will change because you are changing dA. Now which will contradict the CMB observations. To solve the tension, then you have to do something to this formula to compensate for this change in dA that you get by increasing the H0. And you can do this by modifying dA, by modifying late time histories, so that you undo this change in dA done by H0 by modifying the other things. Or you can modify R star, you can compensate by changing R star in the same way. So this is the early universe solutions. For example, early dark energy or introducing new species, or you can just change the phase shift. You can compensate delta dA by changing the phase shift introduced by neutrinos. And it turns out that when you introduce these interactions, it actually does exactly undoes this change in phase shift that is done given by it exactly undoes the effect of increasing H0. So this is shown in here. So red line is the lambda CDM. So this is, I think, the last part, but I will just take 1 minute. So red line is the lambda CDM with free streaming neutrinos. If you introduce interactions, so you stop the neutrinos from free streaming, this thing shifts to this solid blue curve. So now to bring it back to the lambda CDM value so that you want to agree with observations, you have to increase the H0. So the H0 and this phase shift due to free streaming of neutrinos, they work in the opposite ways. So interacting neutrino cosmology with a higher Hubble value H0 is similar to the lambda CDM cosmology with free streaming neutrinos. So that is the takeaway point here. And you can do a more sophisticated MCMC analysis, including galaxy power spectrum from Wiggles's survey. You see that actually the tension in best case, it reduces to 2.1 sigma from 4 to 5 sigma. And you can also do a combined analysis with SLUs and look at how the chi-square improves. And we are one additional effective parameter that we are adding. The chi-square improves by about -9. So that's a good thing. It means we are solving the tension a little bit. One thing I did not talk about, that's in standard lambda CDM cosmology, neutrinos free stream. So their gravitational perturbations decay away. In interacting neutrinos, their gravitational perturbations do not decay away. So they help clustering of dark matter. So dark matter power spectrum on small scale also increases, which is shown in the right panel, which means that the lensing B modes also get boosted, which is shown in this left-hand panel. So I will just stop here. So we may have discovered a new dark interaction in Hubble tension, a non-standard behavior of neutrinos in this Hubble tension. And in particular, it has interesting implications for this gravitational wave power spectrum that we get from inflation, in particular for the CMB B modes. And I will stop here. Thanks.
Thanks a lot for the nice talk, Rishi. We have time for one question. Anyone wants to ask? Otherwise, I can ask, can you comment more? Oh, okay, Anish raised the hand. So you can go.
So just a small curiosity. Do you expect degeneracy with any other parameters like mass sum of the total neutrino masses or something like that? I mean, some other, degeneracies with
so I don't. Yeah, we don't really expect any degeneracies because all of this happening before recombination when neutrinos are effectively massless. So mostly massive neutrinos, they change the dark matter. So if you introduce some mass in neutrinos, then your dark matter omega goes down a little bit. But those things don't really affect this neutrino phase shift or this damping that I'm talking about.
Right. So since I mean by the same logic, you do not expect anything with neutrino hierarchy, right? Whether it's an inverse hierarchy or straight hierarchy, because it has not.
Okay, good. I wanted to ask about the genesis indeed. Thanks a lot again to Rishi. We can move on to Pedro.
Okay, I will stop sharing.
Yes.
Hello.
Hello.
So yeah,
okay.
Let me.
Pedro will tell us about audible actions. I can see your screen, so I guess you can start. The format is again 20 plus 5, and I will tell you when there are 5 minutes remaining. Go ahead,
Okay.
Please.
Yeah, also from my side, thanks a lot for the invitation and for organizing this very exciting workshop. So let me give you a brief outline of what I will be talking about. So I will start with a short motivation of why axion-like particles, or short Alps, are interesting also in the early universe, and in particular then introduce a mechanism by which gravitational waves are produced from such Alps if they are coupled to dark photons in the early universe, but actually after inflation. We'll say a few more words about that. I will present a few new numerical results that we have achieved recently, and also discuss how this and also other models might be able to accommodate the nanograph signal that we have recently got the first hint of. Okay, so what is an Alp? As far as I'm concerned, for the purpose of this talk, this is a pseudoscalar, so a very light particle with a shift symmetric potential, which could be either discrete or continuous shift symmetry. And once this shift symmetry is broken, at least broken to a discrete symmetry, it can pick up a small mass, but it tends to be a very light particle in the early universe. And these kind of particles are interesting, for example, as dark matter candidates via the misalignment mechanism, or also because they tend to appear in many UV theories of extensions of the standard model to explain flavor structures, to solve the strong CP problem, or even like in string theory from these compactifications. Okay, so what do Alps have to do with gravitational waves? Well, there are quite a few connections, which I think all of them I find quite interesting. So there's, for example, the possibility to use black hole superradiance to probe the very presence of very light scalars because they spin down black holes. And there's this intrinsic connection of axion-like particles, which are pseudo-Goldstone bosons, and symmetry breaking. So you have a phase transition, and in principle, phase transitions associated with those models can source gravitational waves. This was a topic that was discussed heavily yesterday. I mean, the whole idea of observing gravitational waves from phase transitions. Instead, what I will focus on here is gravitational waves which are sourced by axion dynamics after inflation. So during after reheating during the radiation-dominated epoch of the universe. And in particular, I will focus mostly on models where the Alp couples to a dark photon, because this is where we get the strongest source. So I'm somewhat off topic in regards to the topic of this session, but in the end, the mechanism I'm using is something that is also well known and well used in the inflationary literature. Okay, so let's get started. So we will simply look at what an Alp does in the early universe. So our initial condition is this axion-like particle, this dot here, the field, which is displaced from the origin after inflation. Yeah, this is kind of the generic, how do you say, initial condition. And then its dynamics is dictated by the equation of motion. So you have the parts which move, the second and first derivative. This is the Hubble damping term. I assume that you can see my mouse. Yes.
Yes, we can.
Okay, very good. You have the derivative of the potential, which is effectively the mass term. And there are two other terms, which for the moment I want to ignore. So in the absence of additional contributions to the equations of motion, what effectively happens is that the Alp will start rolling at the time when its mass is equal to the Hubble rate. Yeah, because then the friction is small enough so that the field can actually move by and get a reasonable velocity. And then if you analyze this scenario a bit more carefully, is that then the Alp kind of oscillates in this potential, and its energy is therefore, converted from potential energy to kinetic energy and back all the time. And if you average this, particle or this configuration behaves like non-relativistic matter. So this makes this axion misalignment mechanism a very nice way of getting non-particle dark matter. Okay. Now we want to see what happens if we add one additional interaction, namely if we couple this axion to a dark photon. Yeah, this is this field X that we're adding here to the equations of motion. Now what happens in this case is that this is an additional source of friction in the equations of motion. So the oscillation of the Alp is damped, and the energy instead goes into an exponential production of dark photons. And one of the reasons why one might be interested in introducing those dark photons is as a mechanism to reduce the Rayleigh abundance, so to make the region of parameter space viable where you would otherwise overproduce axion dark matter. This is something that was pointed out, I think, for the first time in this paper by these people listed here. So, well, why is this interesting besides the effect on the axion abundance? Well, if you look at the dark photon equation of motion more carefully, yeah, what you see is that once the axion starts to move, there's this extra bit proportional to the axion velocity that appears in addition to the momentum squared in the equations of motion for the dark photon modes in momentum space. And this means that this rolling Alp induces a tachyonic instability. There's a certain range of frequencies for which a certain range of momenta k, for which the frequency of this dark photon, of the corresponding dark photon mode, becomes imaginary. Yeah, and that means instead of a nice oscillating mode, you get one mode. Depending on the helicity, you get one mode which is growing exponentially and one mode which is damped exponentially. And this does not happen in a random place, but for a range of modes which are kind of depending again on the velocity of the axion. So this is an effect which is only active until this system has relaxed to a more stable configuration. Okay, so this is why, yeah, typically if you couple a very light particle with a very small coupling to another field, the friction it exerts on this field is very small because the decay rate, yeah, it's tiny. But because of this exponential amplification, this is a very efficient way of dissipating energy. But what this also does is it blows up the quantum fluctuations which are already present in the dark photon field for that particular range of momenta. Yeah, so if you look at the dark photon spectrum, you see that you have this range of momenta for which one of the polarizations has a very high occupation number, while the other one is essentially irrelevant. And since these are fluctuations with a specific length scale, if you plug them into the Einstein equations to compute the gravitational waves source of this configuration, you find that this produces a chiral gravitational wave background. Yeah, and this is what we show here in this figure on the right. It has a very clear peak, which is associated with the range of momenta, which go tachyonic, which again depends on the scale when this dynamic starts. And this is since maybe a lot of people here have more background in inflation, this is very analogous to how this happens also in models of axion inflation coupled to gauge fields. Yeah, there you find the same spectra, just the background is different. Okay. The interesting thing is now that this spectrum, since it's produced in radiation domination, it's not redshifted away by the inflationary dynamics. So this is something we can try to find now. Okay, and that's what we show in this plot here. So as a function of the mass of the axion and of the decay constant, the regions at the bottom here are the ones where gravitational waves can provide a new probe of this parameter space. For example, here below the red line, the LISA experiment would be sensitive to this kind of signal. Over here, SKA might pick up some signal, and then other experiments would go where you expect them to go. And what I think is very interesting is that this really probes a region of axion parameter space, which is very difficult to probe otherwise, because usually your probes come from large coupling. So up here, where the suppression of the axion coupling to the visible sector is not so big, that's where you can have your haloscope experiments and so on, or cosmology constraints. And we really have constraints or ways of probing axions really coming from very small couplings, very high decay constants. The reason that we are mainly sensitive down here is because the axion, it's a simpler energy argument. The source of the gravitational waves is the energy which is initially contained in the axion field at the time when it starts rolling. And this is a quantity which is proportional to the axion decay constant over the Planck scale squared, and then you plug it in then you compute the energy density in gravitational waves, you have to square it again. That's why it depends on the force power of this ratio F over M Planck. Yeah, and that's why we're only sensitive at very small couplings at very large decay constants. And then the peak frequency, that's why you have this region here, depends on the axion mass. Yeah, it obviously depends on when the axion starts rolling. Okay. So that's kind of the first part of this story. Now, there was one more term which we had neglected in the equations of motion, which is this gradient term here. And this is, so we initially assumed that the axion field stays homogeneous while all this happens, so that we only consider the zero mode. And of course, once you produce a significant population of dark photons, they will start to backscatter into Alps fluctuations. And therefore, this gradient term cannot be, will become non-negligible at some point. And then in order to solve the equations of motion also in that regime, you have to do it fully numerically. Yeah, the equations couple again, so it becomes rather difficult to do it in momentum space. Instead, we go back to position space and we put the system on the lattice. But that took another year, more or less, of work. And yeah, this is kind of what happens. So when you compare the solution without this back reaction term and with back reaction, without back reaction, what we show here is the energy density in the axion field. You see here that it behaves like a cosmological constant at very early times, and then it starts to undergo these oscillations. So it starts to scale like matter. And then this is the point where the tachyonic instability starts to kick in and deplete the energy density. And up to this point, the linear analysis and the lattice computation agree very well. And then the linear analysis predicts that the abundance continues to be drop, to be transferred into dark photons. Where instead, if you include the back reaction, you see that the drop-off is much milder, and this is essentially consistent with redshifting until the point when the field becomes massive. And so when the modes are redshifted enough such that these are like massive particles, and then the relic abundance stays constant. Okay, so including these backscattering is important, was also already pointed out for the computation of the relic abundance in these two papers down here. And we confirmed it, and we also explored possibilities on how to readjust the relic abundance, for example, by looking at models where the mass of the axion at the bottom of the potential is either smaller than the overall slope or actually even vanishing. Yeah, these are things you could imagine that you get them by adding another phase transition. Yeah, so you can explore the whole range of axion masses and couplings. And of course, the main question we wanted to answer with our lattice computation is what is the effect of this backscattering on the gravitational wave signal. And this is kind of shown in these pictures here. So these are the gravitational wave spectra, again, from the lattice for different values of the axion coupling to the dark photons. Yeah, alpha for moderate values 40, 50, up all the way up to 100. And the green cross here indicates where our linear analysis kind of predicted the peak and the amplitude. So you see that qualitatively the signal is unchanged. Yeah, I mean, until such a time when we really go to precision measurements of the signal, this is kind of a good enough approximation. But what you also see here is that there is a change, namely the polarization is washed out, but not always. So for the smallest value of the coupling, we considered there's still a huge an order of magnitude difference between one and the other helicity. But as you go to larger couplings, you see that the polarization is washed out. So, you know, if we ever get to see the signal and we can actually measure the polarization, this will give us additional information about the potential source of the signal. The polarization itself is a smoking gun of this scenario. And then in addition, the degree of polarization would allow us to get some indication of this coupling.
Sorry, Pedro, 4 minutes.
Yeah, thanks. Okay, so we can, with this new spectra, we can redo this mass over coupling plot. And you see, and again, show the different regions where experiments would be able to probe the scenario in the future. And there is, again, everything below the curves is detectable. And you see that we're probing some of the region where the axion could be the dark matter and also where the dark photon could be the dark matter. Although everywhere we require rather strong suppression of the axion abundance in order to get to not overproduce dark matter, except for this region over here, which is testable by SKA. Right. Now, two more recent developments in this direction. The first one is that we also considered this mechanism in the for the Relaxion model. This is a model or a scenario where the axion is used to solve the hierarchy problem. So you see here, in addition to a potential which makes the axion roll, there's also a coupling to the Higgs, which kind of scans the Higgs mass while the axion rolls. And then there's a back reaction term which makes the axion stop when the Higgs mass takes the small observed value that we see in nature. And in some region of this Relaxion parameter space, adding a dark photon as additional source of friction is essential to keep the axion trapped at the right value after reheating. Yeah, because after reheating, this back reaction potential goes away, the axion would start to roll again, and it shouldn't roll too fast, otherwise it would spoil the mechanism, it would spoil the solution of the hierarchy problem. So obviously, it was a straightforward question to ask whether this, also in this case, an observable gravitational wave signal is produced, and the answer is yes, otherwise I wouldn't be showing these plots. So you see here in white and in these blue, green, and purple colors, this is the viable region of this Relaxion model, and the colored region are testable by these various experiments. Again, here we also show where we would be able to fit the nanograph signal. Yeah, so this is, I think, a rather exciting possibility that we are seeing there a solution to the hierarchy problem. But, well, okay, it's a little bit optimistic, of course. Another thing we have been investigating recently and are currently preparing for publication is the question, what if we don't use the potential energy of the initially displaced axion, but if instead we start the dynamics with a large kinetic energy, so a large phi dot. And this allows us to, and that of course means we don't need these very large decay constants, because we can just instead put a lot of kinetic energy in the field. And in that case, we can get a detectable gravitational wave signal from this axion dark photon system, also for much smaller decay constants. So this is also something rather interesting we're investigating right now, which was also pointed out by another paper recently that I put down here. And you see here again, we find lots of parameter space, which is testable. In this case, MS and SI are kind of parameters which belong to the UV completion that generates this large initial kinetic energy. So this is, yeah, you replace the high scale by another heavy or largely displaced particle. This observable gravitational waves from this scenario here are even consistent also with axiogenesis. So you could even be more optimistic and say this will allow us to probe both a mechanism that gives dark matter and baryogenesis, which is kind of exciting. So I will very briefly mention these nanograph results. I think this was already mentioned, yes, on Monday and Tuesday. The nanograph saw a hint of a gravitational wave signal at very low frequencies. And obviously we can ask, this scenario here are even consistent also. Yeah, that was a funny. So echo? I think someone has his, yeah, thanks. Yeah, so we try to ask whether this can also be fit with a broken power law signal, in particular with this audible axion scenario, but also with phase transitions, either runaway, so envelope approximation, or non-runaway sound wave contribution. And well, you kind of can see here that the data is still uncertain enough that everything can provide a reasonable fit, although phase transitions tend to do a little bit better than the axion model. What I found rather interesting is that already from this very raw and not conclusive data, you can do a rather good extraction of the signal of the model parameters. So in this case, for the audible axion, because it only has two free parameters, the mass and the decay constant, you can really do this fit and find a rather narrow region. So this points to an axion of something like 10 to the minus 13 eV, which is also in some tension with constraints from ineffective, because we're producing all these dark photons. Yeah, so it was, I mean, it was an interesting exercise to see how much we can already learn from such a rough signal or potential signal. We did the same exercise with phase transitions for different values of the transition parameters. Also there, you of course find a good fit, and it points to a phase transition somewhere above the MEV range, which again is very interesting because that's a region where you can't do whatever you want. If you want to have a model there that undergoes a thermal phase transition, you have to make sure that afterwards you get rid of all the stuff before and not screw up BBN or ineffective. Yeah, so this is a small model building challenge that we have left to solve, how to really populate this region with actual models and not just phase transition parameters. Okay, so this brings me to the summary. I hope I didn't go over time too much. I think here we all agree that gravitational waves offer a unique window into the early universe. We've been studying in the last few years a new way to probe axions or axion-like particles. This mechanism, as I argued, this tachyonic particle production is frequently used in model building, also in inflation and reheating, and we can now do precise numerical simulations of this scenario. And finally, I think it's very interesting to explore possible explanations of the nanograph data, also because there will be more data in the near future. So this is very exciting. Thanks a lot for your attention.
Thanks a lot, Pedro, for this exciting talk. Any questions now? If not, I can start. I wanted to ask you, do you have an idea of the maximum frequency that you can get?
Yeah,
because
so
typically in inflationary models, you have a cutoff, right? That comes from the end of inflation, say, around the gigahertz region. In this case,
oops, I think I closed my window. Well, I can answer. Yeah. So I think I only showed the spectrum once. Yeah, it's rather peaked, and then I can shift the peak by changing the axion mass. And we explored all the way up to masses which would be detectable by the Einstein telescope. So something like hundreds of hertz.
Okay, is there any abstraction in going?
I think at some point, I mean, this is a region when the axion mass is already a few hundred GeV. So, I mean, you get more and more into the region where it wants to behave like a particle and not like a field, and then this whole discussion doesn't apply anymore. Yeah.
Okay. Questions? I don't see hands raised, so maybe I can ask another one. In this case, so in the case of inflation, you have only one polarization, which is excited, because basically the inflaton is moving only in one direction. You have one sign for the speed. Here, I guess it's oscillating, so you produce both of them.
Yeah, that's a very good question. Yeah, so I mean, what happens at the end is that it's still the same argument still applies, yeah? Because the first oscillation is so important. Yeah, okay. Because it's a multiplicative thing. So you pump one set of modes, and then on the way back you amplify the other modes, but then your amplitude is already much smaller, and it goes into the exponent.
I see.
Yeah.
Okay.
So it's this parity symmetry breaking that you have effectively from the initial condition, the same as in inflation. Yeah.
Okay, thank you, Anish.
Yeah, so I just wanted to ask you. So, do you expect any significant difference if you consider non-abelian gauge fields instead of abelian dark photon-like fields? Because the field itself will have some self interactions which can backward, right? So maybe you will get some smoothing, or maybe even the nonlinear effects getting smaller. Yeah,
so this is something that I think also, at least for inflationary scenarios, is being studied or has been studied. I think there's papers by Zach Weiner and company, and they do find similar signals. I think if you do this so in our scenario, if you do this in radiation domination, of course, once you start producing the gauge fields, because of their self-interaction, they will acquire a thermal mass. So my expectation is that the tachyon will be quenched much quicker. So that it should make a difference.
Yes. So you mean the spectrum will be different? The spectrum that you showed, it goes up and cuts down, that will be different. Okay.
Yeah. I would think that this tachyonic phase doesn't last for as long, and therefore, probably the signal would be smaller. But we haven't done the mass yet, so I think it's something that we should probably investigate. Yeah.
Okay, good. I guess we can move on. Thanks a lot, Pedro, again.
Okay,
and we go to Anupam Mazumdar. Can you share your screen? There we are. Yeah. Anupam will tell us about classical versus quantum divide of gravitons in cosmology. Again, the format is 20+5, and I will tell you when 5 minutes are remaining.
Okay.
Go ahead. Thank you.
Thanks. Thank you very much for to all the organizers for inviting me to give a talk. So I'll talk about classical versus quantum divide of gravity in cosmology. And my talk will be slightly different from the rest of perhaps the speakers, in the sense that I will discuss only model independent issue but in a model dependent way. It's completely model independent. And with very simple coupling, which is universal coupling, which is gravity. And the question is a fundamental in nature, that how do I know whether gravity is classical or quantum? How do I know whether gravity can be alive and dead simultaneously? How can I see gravity's this Cheshire witness of Cheshire cat, that it has a quantum feature? And whether primordial gravitational waves will help us telling that, or cosmological phase transitions will help us telling that, or perhaps we have to go for lab-based experiment. So just to conclude also, because I mean, if you don't want to hear majority of the talk, that's also fine. In my opinion, it will be extremely hard from cosmology to infer this question. Maybe we have to go for some lab-based experiment. And if time permits me, I will talk about that lab-based experiment. So this is the plan of my talk. I'll talk about a little bit about gravity, just to set the base. Then I'll go on to cosmology. Then I'll talk about cosmological phase transition. And if time permits me, I'll talk about how to test quantum gravity, perhaps in a laboratory. And this is the sextet I have just created by myself. I think it's just in a chronological order. You can read through it, and perhaps you will understand why this remains is a hard question to tackle, which has a history of more than 350 years now, perhaps close to 350 years. So gravity is unique. It's unique in the sense that no other interactions of nature has this unique feature. If you place a mass, it doesn't matter whether it's matter, antimatter, charge, uncharged. As soon as there's a mass, it creates a gravitational radius, which is given by my Schwarzschild radius, which is m over m Planck squared. So, you cannot see such feature in either QED or QCD. So way back in 80s and 90s, Dyson argued many times, not just once. He inspired many discussions. Way back when he was quite active also in Princeton. He asked the question, what will it take to detect a graviton? You know, we have detected standard model particles. Of course, the interaction for gravity is extremely weak. And I'm just revising his argument. So you can compute for any mass, it could be proton mass or electron mass. You can see the cross section, which is very tiny because G is a very tiny number. So let's say for the argument's sake that I take the mass of the proton, so graviton hits the proton and I want to see how what is the interaction rate. And so if you want to have a detector with the length scale, I call it lambda, with certain length scale, NP is the number density of my, let's say proton for argument's sake, and sigma is my cross section, which enters here. It has to be not maybe roughly of the order of 1 in order to make some detection. Otherwise, it will hardly detect anything. And it turns out that even for Earth-sized detector, if you take Earth's radius, and let's say the Earth is filled with just protons, and you find that you know the cross-section, and you find that no, it's very hard to reach order 1. You have to go for even bigger detector, something like Jupiter or something of that size. But Jupiter, but also you have to have a very large density. So we would need some indirect methods. So then this leads to the automatic question, could cosmology help us settling this question? Because such a fundamental question, it has to have some answer. And since we have been looking towards cosmology for many years now, could cosmology help us? So let's do, just to set the base for the talk, some of the things which you all know. It's the bread and butter for all cosmologists. So so what you do is that you take any background. It doesn't have to be Minkowski. You can take any background. You perturb that background, and if you perturb that background, so this is your graviton h mu nu, fluctuations in gravity, if you like. You can decompose that fluctuation into transverse and traceless component, which is h perp. You have the vector component, which is transverse, and these are the scalar component. And these are the properties which it follows. It obeys. For gravitational waves, this is the transverse and traceless component which propagates in space-time. It's essentially the on-shell graviton, which has 2 degrees of freedom, which many people have discussed already in this conference. When you talk about gravitational potential, when you're mediating gravitational potential in presence of some conserved current, conserved sources, then you also talk about the off-shell degrees of freedom, and there you have both the perp, the h mu nu perp, which is the transverse traceless component, plus the scalar component, which propagates. And the scalar component is this component. It's a combination of B and H, the 2 scalars. And these are 6 degrees of freedom, which propagates. And then you can do it around any background. You can, if you want, you can do it in Minkowski, de Sitter, ADS. You can do in FRW background or any background, even maximally symmetric background. Beyond maximally symmetric background also you can do this. So let's talk about the gravitational waves. Very simple with quantum initial conditions. This is the first thing which I mean many of our undergrads and our PhD students learn. So it's nothing very fancy. You can look into the second order fluctuations of your action in terms of graviton, just Einstein-Hilbert gravity, nothing beyond that. And this is your scale factor of the universe. In this case, it's FLRW universe. And you can do the mode decomposition. And at the end of the day, you can solve this equation in terms of Hankel function, but in a limit when this k is your wave number, tau is your proper time. In the limit when k tau goes to very large, you can write it down in this plane wave kind of solution, where alpha k and beta k are your Bogoliubov coefficients. You impose the quantum initial condition. You can determine the alpha k and beta k by imposing the quantum condition. And that initial condition could be Bunch-Davies vacuum. If you don't like Bunch-Davies vacuum, you can use other vacuum. You can motivate many other vacua, and you obtain this 2-point correlation for the gravitational waves, which is given by your Hubble expansion rate during inflation divided by m Planck square. It's very simple. Now you can ask the question, can I reach the same conclusion just by doing classical physics without invoking any quantum initial conditions? And the answer is yes. It is possible, and it's something which a couple of minutes ago I saw Amjad Ashurian. He was present in this conference with whom I looked into it way back in 2012. So you do the same decomposition, but now you impose the reality condition. You say that my Bogoliubov, there's these coefficients alpha and k and beta k. These coefficients, Bogoliubov coefficients, have a reality that they follow the classical condition, no longer initial condition. You can compute the power spectrum, and that power spectrum will have both alpha k and beta k, the whole square divided by h square over m Planck square. So there's no Bunch-Davies vacuum. However, if you really want to mimic exactly like the previous subsection of this result, then you can choose alpha k and beta k. Of course, it's a classical condition, so you can always raise your hand and say, who gives you this classical condition? But someone who is very agnostic about the situation, about the physics, of course, can say that, look, if I choose some combination of alpha k and beta k, I can always mimic the answer below. But I will have an even simpler argument where I will show that essentially none of these perturbations really have any quantum feature. And the reason comes with very simple physics, as simple as photons. If you have a single photon, you know the photon is quantum. You can put the photon in a cavity, and people have done this kind of experiment. You know it's quantum behavior. But the same if photon, if you have laser, you have many photons. If the number of photons is way too larger than one, it has the classical behavior. The classical description of photon comes in. In a very similar way, you can distinguish for graviton also, as long as the graviton is very small, they have the quantum feature, but if the number of gravitons becomes way too large, it approaches towards classicalization. So a very simple calculation one can do. Suppose you take a mass, you write down, let's do the non-relativistic calculation. We can do the relativistic calculation as well. And you write down the Lagrangian for this non-relativistic particle. You do the perturbation around say Minkowski space. Again, you can do perturbation around any background, but let's do a very simple exercise computing around the Minkowski background and take the non-relativistic limit. For this, the best thing is to go into the Fermi normal coordinate system, the coordinate system on the particle itself, and you do a very simple perturbation. So quantum gravity, I mean by perturbative quantum gravity, nothing beyond that. You immediately read the interaction between matter and gravity. So this is your graviton, and x is your distance, minimal distance. This is nothing but coming from the equivalence principle, which tells you that in the limit, when x goes to 0, you can have your Einstein's lift. You can get rid of your any acceleration or gravitational acceleration. So the interaction essentially effectively vanishes in that limit. So what you can do is that now you can demand that, let's say the graviton, you can have a Fourier decomposition of the graviton. Let's argue that the graviton is quantum. You can impose the quantum conditions. The modes of the gk and g lambda k follows your this condition, and you can write down the gravitational Hamiltonian. Okay, and now you can write the same gk in terms of just by redefining two variables p and y. These are just a combination of creation and annihilation operators. So you know the interaction between matter and graviton, and what enters is this the graviton Hamiltonian and the interaction Hamiltonian. And now you ask a very simple question, and this is a legitimate question to ask. Nothing stops me from asking this question. Suppose I take the matter and I say, I trace out all the matter degrees of freedom. So I demand that I trace all the matter degrees of freedom. So I take average of matter. Okay. Then what happens? Then what I find, very simple observation, what we have found is that the graviton, the Hamiltonian of the graviton simplifies. And not only that, so this alpha k is now is just a constant because mass is constant, omega is roughly some number, and this is number, and this becomes your number. X squared becomes some number. Okay. But most importantly, what you find is that the gravitons are no longer in a ground state. You start with the graviton in a ground state, but once you trace the matter, what you find that the gravitons become excited. It becomes displaced ground state. So the ground state self shifts. And this is nothing but, this displaced ground state is nothing but a coherent state in quantum mechanics. For this coherent state of graviton, you can compute the graviton occupation number, and that occupation number comes out to be, with some algebra, is nothing but, as I showed you in your previous page, you can find it out. But interestingly, if you now sum over all the momentum modes, so this is what you need to do. You sum over all possible momentum modes, which appears in CK because CK contains this omega and omega k cube. So when you do all the integration, what you find very interestingly and which amazingly, which there's no connection between these two subjects, that the number of gravitons bounded by the area law of your mass. As I said, that as soon as you place a mass, it has a Schwarzschild radius. So somehow the gravitons knows this, and it's precisely because of this various typical interaction which gravity has with matter, minimal interactions of graviton. You generate the area law, and you know that the Bekenstein way back in 1980s has already placed a bounds, very interesting bounds on entropy of a system, gravitational system for a self-gravitating system, which is given by energy times the radius. And for a black hole, ER is nothing but 2gm squared. Now, number of gravitons, now let's forget these coefficients. These are not very important for argument's sake. It's nothing but proportional to gm squared. We're nothing but m over m Planck squared, nothing but the ratio between your gravitational radius divided by your Planck scale. And the same, as I said, the same thing will hold for relativistic matter as well. Now, this case becomes very similar to what Gia has been talking about. Giadwali and Gomez, they have been talking about for a long, long time now, the corpuscular gravity. So we have actually derived the corpuscular gravity in some sense that in presence of large number or large occupation number of gravitons, what happens is that effective coupling. So this is n gravitons sitting here, and they're interacting with each other, and it's a leaky system. After all, graviton can leak. Nothing, I mean, from quantum mechanical, you can leak the graviton. But in presence of large number of gravitons, what happens is that you develop an infrared scaling gravity. And that comes essentially just from the simple algebra, because ng is nothing but m over m Planck the whole square, which is rg over L Planck the whole square. Now the rg, the fact that, as I said, the gravity has this interesting feature that it recognizes the Schwarzschild radius. And if you consider that to be your new scale of physics, m effective, let's say, then the m effective will scale with ng. If ng is large, m effective will become smaller and smaller compared to Planck scale. So effective coupling for graviton, every vertex, what it sees is that not 1 over m Planck square, but it sees with this number ng over m Planck square.
Sorry, Anupam, just to say 5 minutes to go.
Sure. Now, again, you can ask, just to give an example, since my time is running out, so take an electron mass. Electron mass, if you place the electron mass here, you get 10 raised to minus 44. Electron is inherently quantum. But the same thing if you take for black hole of solar system, you get large occupation number, which tells you that the graviton becomes, the black hole becomes effectively a classical system. So same argument you can argue for de Sitter space, and you can show, since I don't have much time, for a coherent state, you can show that this very interesting behavior happens. The fluctuations, because in large n limit, the fluctuations are suppressed by 1 over square root of ng. And this is nothing but, in the case of de Sitter, is nothing but h over m Planck, which is roughly 10 raised to minus 5. And the 2-point correlation for the graviton will be nothing but the square of this quantity, which gives you 10 raised to minus 10. And which tells you essentially, effectively, that although this is a very tiny number, but effectively the system we are dealing with is an inherently classical system. I will skip the fundamental strings and cosmic strings, and it's very interesting. You will find that the strings are inherently quantum system, but I will skip that. But let me talk a little bit about the phase transition in the last couple of minutes. Actually, you can argue in the same way, because after all, whatever phase transitions you're talking about, whether it's a first order, second order, or a smooth phase transition, these are all self-gravitating system. Yeah. So there is a characteristic frequency, which is defined by omega, which is different from your Hubble expansion rate. It can be greater than h, or it can also be less than h. So how do you envisage the phase transition in the process that, so you have a phase transition, now you replace the phase transition by number of gravitons, ng gravitons, and you shake the box. And if you shake the box, what will happen? You will lose some gravitons. Yeah. And you can compute that again from the arguments which I have shown you before, that effective coupling of graviton becomes very, very tiny in presence of large n. This is a collective effect which was already been observed by Giadwali and Gomez. So you can compute for any phase transition. You know that how the graviton will decay. You know the interaction, and it decays with the frequency, which is omega cube. Okay, you can compute the rate of energy loss. You can compute, this is the energy loss expression, which goes as a quadrupole moment, this is the definition of the quadrupole moment. And what you can find that you can compute in this process in a very model independent way, irrespective of what kind of phase transition it is, the first order, second order, smooth crossover, whatever, is given by a very simple expression, which is governed by your moment of inertia, I square, the frequency, and the Hubble expansion rate, and the number of gravitons it contains in the system. And what you can do is that you can now compute the gravitational wave, the omega, and it is bounded. Of course, there are many coefficients which I have neglected for the argument's sake. So it's an upper bound. It's always bounded by omega cube over h cube. So irrespective of any model you choose, you will get this bound. Now, as I said, that now you can ask the question, what are the conditions which will tell that omega is less than h and omega is greater than h, where f denotes the time when the phase transition happens. And if you can convert that into observable omega today, which is roughly 10 raised to minus 5 times this original omega. And you can show that I'll just give, you have to take my word and you can go through the papers, that any phase transition, which is very smooth, it's not a first order phase transition, typically omega is less than h, 10 raised to minus 1, 10 raised to minus 2. And again, you can get the omega today roughly around the bulk part of 10 raised to minus 8 to 10 raised to minus 11. But the phase transition happens, which is strongly first order, that has a very interesting property. The property is that the decay rate, you can compute from this n gravitons leaking, essentially gravitons, the leaky box. And for a bubble nucleation, the decay rate has to be bigger than h, and that tells you that omega f has to be bigger than h. So in principle, in a strong first order phase transition, you can get of course, this upper bound as maximum you can reach is roughly 10 raised to minus 5. So this provides a very interesting possibility that maybe LISA or in future gravitational wave detectors can definitely has a sure shot that it possibly can detect these kind of gravitational waves. But nevertheless, this is highly a classical system. So I will skip the last part of the talk. The only way you can test it is through kind of like a LSC kind of detector. You need a LSC kind of physics. You really need to bring particles and collide them and measure some properties which are inherently quantum, which are known as entanglement property. Since I do not have much time, I guess I will skip to this part of the discussion, but maybe one can look into some of these aspects, how to detect graviton or quantum nature of graviton in laboratory. And I'll skip to this part. And let me just conclude that if you really want to test quantum nature of gravity, it is extremely, extremely challenging. So extracting quantum gravity signature from cosmology will be extremely hard, if not impossible. It will be extremely hard. It's just because of the large NG effect, which I've argued. There is a very interesting possibility emerges, which is called QGEM. It's based on certain properties of quantum physics, entanglement properties, which has very interesting possibility of detecting it. But since I didn't have much time, I'm not going through this part. If you have any question, you can ask me later on. Thank you very much.
Yeah, thanks a lot, Anupam. Very interesting. Any questions about Anupam's talk? Well, I can ask one. I've seen that you have this paper with Andrew Geraci. Are you using this levitated sensors idea to?
I see. Yeah. So this is the idea, very simple idea. So you take two Stern-Gerlach apparatus, and this Stern-Gerlach apparatus mimics your vertex, where you bring two masses. So essentially, in LHC, you take proton, and you collide them. Here, in LHC, is a very high energy collider, but here it's a very non-relativistic collider. You bring two particles very, very close to each other, but what you do is that you place them in a quantum superposition. In LHC, your momentum is very well known, but here, what you do is that you do the opposite. You place the particle in a spatial superposition. So you know the spatial positions extremely well. And you bring in two such Stern-Gerlach apparatus, so the masses can be here and here. The masses can be here and here. And when you interact them, then you can, essentially, it's a scattering diagram. You can look into initial and final states, and you can look into the entanglement. And through entanglement, you can witness whether gravity is classical or quantum.
I see. Thank you. Any other question? If not, I guess we can thank Anupam. Thanks a lot. And we can end this session here. In principle, we should reconvene like in 5 minutes, but Anish will tell you.
Yes, thank you for the nice talks. We had Francesco from Cambridge chairing this session. And let's take 6 minutes break. We reconvene at 4:10 Central European time. And we request all the speakers to be present during the discussion session if possible. We'll take some of the questions and discussions that were not possible during. Okay, thank you.